At the back of the paper here in question 10, there's a bit of a kicker in quite a challenging question. So we're given here the diagram which shows a function for values of x between -1 and a, where a is greater than 1. And we're told that this line L is the tangent to the graph of f at the origin, and we know that the point AB lies on the line L. In part A1, we're told that given the derivative f dash x equals 2a squared minus 4x squared all over root a squared minus x squared for these values, find the equation of L. So we know that at 0, the gradient will be 2a squared minus, now this is going to be 4 times 0 squared, which is obviously just going to be 0, all over root a squared minus 0 squared. So we can see that that is going to simplify to 2a squared all over a, because technically there could be a plus or minus, but we can see at this point the gradient is positive. So that is going to simplify just to 2a. So the gradient at the origin here is going to be 2a. So we can just use the formula y minus y1 equals mx minus x1 to find the equation of the line at that point, because we know at the origin y1 and x1 is 0, so that's going to be y minus 0 equals 2a x minus 0. So that leaves us with the line y equals 2ax. Part 2 then says hence or otherwise, find an expression for b in terms of a. So we've said that the gradient at the point 0 here, using the gradient function, is going to equal to 2a. Okay, so m equals 2a. But because we have got a straight line which goes through the origin, and we know that the point a comma b is on it, we know that this height here is b and this distance here is a. So the gradient can also be expressed as b over a. So I can rearrange that in terms of b to say that b equals 2a squared. Part B asks us to show that the area of this shaded region here is 2/3 a cubed. Now, we know that this function f of x, is 2x root a squared minus x squared. To find the area under the curve, effectively then we are going to need to integrate this function, so integrate 2x root a squared minus x squared with respect to x between these 2 points, a and 0. Now, at first glance, this looks horrible and pretty problematic. However, remember that when we are multiplying two functions, there is often a shortcut which will enable us to integrate, and that is in the instance in which we can use substitution. So let's just have a look here if we kind of get rid of this nasty expression here by writing u is equal to a squared minus x squared. Now, when we differentiate that, we get du by dx is going to equal to negative 2x, which we can see is pretty much the same as what we've got here. So we can, in fact, write this as negative, because we've got a negative here as opposed to exactly 2x. So take out the negative, and then that is going to give us, we can express this as u to the power half, and we know then that du by dx is negative 2x, so if we've got here 2x multiplied by dx, that would be the same as du. So we've got, we want to integrate u to the half du between a and 0, and therefore we are also going to need to change the limits. So if we've got a here, because we're integrating with respect to u, we need to substitute a into here. So u is going to equal a squared minus x squared. So here our input is a, so this is going to be a squared minus a squared. So we're going to integrate u to the half between, this is going to be 0. And if we do the same then for this 0, so if we take in 0 and substitute in here, that's going to give us a squared minus 0 squared, which is just going to be a squared. So if we are integrating this with respect to u, it's going to give us u to the 3 over 2, and then we'll need to multiply that by 2/3. So 2/3 is a negative outside, remember? So negative 2/3 u to the 3 over 2 for 0 and a squared. So that's going to be negative, if we substitute in 0, that's going to be 0 minus 2/3 a squared to the power 3 over 2. And we should see here that this will cancel out, so we'll end up with negative, or negative negative, or just positive 2/3 a cubed, which is what we are asked to show here. In the final part then, we are told that the area of triangle OPQ, which is this region here, is some scalar multiple k of the region that we've just found out, AR. So the area of AT is clearly just going to be the area for a triangle, so that's going to be half AB, so that's going to be the area of the triangle there, is going to be equal to some scalar multiple of AR, which we've just worked out was 2/3 a cubed. So if we just take B, and we can express that in terms of A. We were asked to do that in the first part of the question. So we know that B was, or could be expressed as 2a squared. So I can just rewrite this as half a times 2a squared is equal to 2/3 k a cubed. And simplifying this then, I will end up with a cubed equals 2/3 k a cubed. So therefore, this value here, 2/3 k, must equal to 1. So therefore, I can solve for k, which must equal 3 over 2.